7.1 Graph and exponential functions. So first let's talk about what an exponential function is. An exponential function is a function where the variable is a power. So it's something like 3 to the x. So variable is the power. That's an exponential function. So it's going to be something to that effect, or something to this effect. So let's graph a function like that. Now, an exponential growth function is particularly when that base, the b right there, is greater than 1. That's what makes it a growth function. So let's graph one of those to see what it looks like, as I like to do. So let's graph y equals 2 to the x. There's my straight line, x, y. Let's do -5, -2, -1, 0, 1, 5. Who needs that -2? Right, so we're going to plug that in and get 2 to the -5, which is just 2 to the, sorry, remember the negative just flips it, 1 over 2 to the 5th, which is going to be 1 over 32. 2 to the -1, that just flips it to 1 over 2. 2 to the 0 is just going to be 1. 2 to the first is just going to be 2. And 2 to the 5th is going to be 32. So let's graph this. Let's see what it looks like. Look at my shapes. I proved I can't draw straight lines, so let's do this instead. So that. Okay, and then we're going to do, let's look at tally marks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3, 4, 5. X and Y. So let's plot this thing. So -5 is 1 over 32. So here's -5. 1 over 32 is basically 0, so that's a little bit above the x-axis. Above it. -1 goes to 1/2, so -1's like right here. 0 gets you 1. Y-intercept. 1 gets you 2. And then 5 gets you 32. So 5 is all the way up here. Let's draw it. So something to that effect. And that's what an exponential graph looks like. It's growing up. Like you want this to be your stock, basically, right? It's constantly going up. So an exponential growth function, like a basic one, looks like this. Should be a little closer to the line, but yeah. So you can add that to our list of growing functions. A couple things I want you to point out. Notice it never crosses the x-axis. It never even touches the x-axis because you can't. No matter what power you plug here, it's going to be a power. And powers don't make things 0 and if they don't make them negative, right? All I do is flip it. So you can never touch the x-axis, you can never get below it. So it's always me above it. Slightly above it. It's a little too far. So that's an exponential growth function. That's what they show right here. And they do an example. We did this example already. I'm going to do it real quick. Try to cross to that one. Looks like this. One thing I didn't do, I forgot to do domain and range. Let's do domain and range. So domain, farthest left is -infinity, farthest right, arrow, infinity. It's always going to be the domain for an exponential function. The range is interesting though. Lowest is 0, but I can't touch it, and never actually hit 0. So lowest is actually 0 with the open parenthesis. And then highest is an arrow, it's infinity. So that's the domain and range for that one. Again, we do this based on the graph. -infinity, positive infinity. Lowest is 0, but you actually can't touch it, so it's not a bracket, it's a parenthesis. Low infinity. Okay, so now we know how to graph a basic one. You know what's next? Let's add all the stuff to it. So as we always talk about, inside, in this case, inside is the power. Inside moves the x, so it's left and right. You do the opposite. Outside actually has a special meaning in this case. Outside is a y value, and we follow. Right, so let's go up and down. Inside goes left and right. There's actually one more thing with the outside function. You could kind of tell the one we did here. There's no outside function. It was +0. That's what we call a horizontal asymptote. And we'll talk more about the horizontal asymptote next chapter, but I don't want to introduce it to you right now. It's a line like right here. In this case, it's a line that you can't cross, but that's not always true. Even on this one, it was the same one, I guess. So +0. Right, so that's your horizontal asymptote, is that y equals 0. So in this case, since it starts at 0 and you add k to it, the horizontal asymptote is always at y equals k. So if it's nothing there, it starts at 0. So again, horizontal has the k has two things, it moves up and down. That's also horizontal asymptote. How about the number in front? Number in front to be special this time. It still has to do with how much of a, like, kind of a shift it has, how much of a stretch it has. But also in this case, A is always going to say it's your initial y-intercept. That'll make more sense in a second. That's our initial y-intercept. Before we start shifting it, that's how much initial y-intercept is. That's how much your y-intercept is. It's also, you can think about it, it's the distance from the horizontal asymptote, if you want to think about it that way. Either way is true. And like always, if A is negative, it does reflect, it does flip. If at the negative A, it does flip down. And if A is greater than 1, it's a vertical stretch. If A is less than 1, it's a vertical shrink. So that's all still true. Keep in mind, we're doing a growth function, so in this case, B has to be greater than 1, and that makes it a growth function. Other than that, it does affect how stretchy and shrinky it is, but we're doing sketches here. And I'll show you what the decimals graph. So let's look at this one. Let's graph this one. So first thing I want to notice is a growth or decay. You can look right here, it's a growth. So if I have my graph here, it's a growth. I want you to figure out a couple of things. What's your initial y-intercept? So what's A? A here, there's no A in front of this, so it's a 1. So I'm initially going to cross out 1. My horizontal asymptote is 3, so you move your whole graph up 3. So my vertical shift is 3, so you move your whole graph up 3. So instead of crossing it 1, you cross that 3. 1, 2, 3. It's like right here. And your asymptote's at 3. One last thing, I got to move it left 1. So again, we started right here, right? That's where our point was. I got to move it up 3, 1, 2, 3, and then left 1. So right here is actually my point. It's a growth function, so it's going to look like this. You can't go below the asymptote. You can't hit it and you go up. That's a basic version of this graph. So again, we're doing a sketch, and that's a basic sketch. My domain, farthest left is the arrow, farthest right is the arrow. Negative infinity, positive infinity. My range, my lowest is 3, I can't hit it, but 3 to infinity. So that's what it looks like. Let me show you something on Desmos real quick. So we have y equals 2 to the power of carrots x plus 1. X plus 1 to the growth function, and then on the outside we're going to go plus 3. So like that. I want you to see that. So it crosses at 5 like ours did. Hit 1, 2, 3, 4, 5. Well, then cross and go perfectly. But it does hit at -1 and 4. Right? -1 right here and 4. -1 and 4 hits right there. And it looks like our graph. Just our graph's more of a sketch. Okay, next one. Oh, that's one I want to show before I move on. What does the B do? So what happens if I change this to, let me copy and paste. And I change that from a 2 to like a 4. Right, so it still hits at 1, 4, but, or 1, -1, but it's like, it's a vertical stretch to it. So I change that to, whoops, to a 6, right? Just get stretchier and stretchier, thinner and thinner. Okay, now let's go back to this one. Same idea. So let's draw, like, what's my table at? Okay, so let's find our A first. A is this. A is 0.25. My B, all I care about is greater than 1, it's a growth. Then I have my vertical shift, and also my horizontal asymptote. So normally I would cross at 0.25. Right, that's what that thing does. But then we're going to go move down 6. So -6 from asymptote's at. And then we cross at 0.25. Then we'll go down 6, so it's going to cross like right here. If you want to think about it, it's 0.25 above the vertical asymptote. Just like how this one was 1 above the vertical asymptote, but then we moved it left. There's no horizontal, there's no moving left or right. So all we do now is graph it. So graph looks like that. Again, we're doing a sketch. So something like that. If I got Desmos, do the same thing. It's a little bit harder to graph in this case. 0.25. Oh, I need a multiplication button. Times, what is it, 4? Minus 6. Okay, so we get that. So it looks like that. Let me zoom out so you can see a little better. So it crosses at a little bit above -6 where it crosses. Now if I knew another one, I want to show what happens if I change this 0.25 to like a 5. So what it really does is it fixes the y-intercept, because now instead of crossing at 0.25, we crossed at 5 originally, and then we moved it down 6. So that's what the A does. It actually affects your y-intercept a little more. It still makes it a vertical stretch or shrink, but actually has a bigger effect on y-intercept. So that's what the A does for exponential functions. Let's do another one. So this one here, I'll make the table again. So again, first thing we're going to do with this is go, okay, is it growth or decay? It's a growth. And then I would normally cross at 3. That's my A. A is 3, so that's your initial y-intercept. So 1, 2, 3 is right there. And then you have right here at 8, you have a vertical stretch, vertical shift of 8. Positive 8 plus 8, which means your horizontal asymptote is at y equals 8. So 1, 2, 3, 4, 5, 6, 7, 8. Now you have 2 ways to think about it. You could either go, okay, remember my A is 3, so it's either 3 above the horizontal asymptote, so 1, 2, 3 right there, or it's initially at 3 and then you move it up 8. Either way, you get the same spot at 11 up here. Again, we're just doing a sketch, so now I know it's a growth, so you can't go below this line. Go, you hit it, and you go up. So that's our graph. Domain and range real quick. Domain's all row numbers, negative infinity to positive infinity. Right, because farthest left, farthest right. Range, low to high. My lowest is 8, and you're going all the way to infinity. So 8 to infinity. Remember, 8 has to be a parenthesis because you can't touch the line. So that's that. That's how you graph growth functions. Now let's talk about application problems with growth functions. So a lot of things actually grow exponentially. This means it has a really fast growth. And the way we look at it, I think this is bad. It's like this. So AT equals A times B to the T power. Here's the thing about B though. B is the growth factor. All that means is how much you're talking about, how much what rate you're growing by. So B is our growth factor. So the way we find B is very simple. It is 1 plus R if it's a growth, where R is a rate, increase or decrease, and 1 minus R if it's a decay. So the key thing to keep in mind here is we always start at 100%. That's what the 1 is, start at 100%. So it's like you have a job, you get paid $50, let's go $50. And the boss will give you a 3% raise. So if I ask you how much you make now, you're not going to be like, oh, I make 3%. I mean, you're not going to say, what's your rate now? It's not going to be 3%. Compared to before, it's going to be 103%. Right? This was considered 100%. That's how much you're normally making. Normal is always 100%. If you raise that 3%, now you're making 103% of what you made last time. Not 3% more you made, not 3% last time. That's why the rate is 100. That's why it's 1 plus R. Your current rate's 100, and then you add the increase. Right? So you don't just go with 3%. 3% your increase, but your rate, your going rate's 103%. Because you're 3% more than what you did before. So that's the idea. So let's do an example to make it easy. So again, this is our formula. And then in this case, A is always the initial amount, always. And B is the growth rate. No matter the way the B works, it's always 1 plus R, 1 minus R if it's a decay. right? So you always start at 100%. If it goes up, add the r. If it goes down, minus the r. A is your initial amount, and then t is time. So look at this problem here. If a cost of painting has gone up in value by 2% each year, so my r is 0.02 since 2010. It initially costs $15,000. How much will it work today in 2015? So old problem. So the idea here is, let's write it down. Y equals, my initial amount is 15 grand. My growth rate, so we got to figure out. Now B is 1 plus R. So in this case it's 1 plus 0.02, 1.02. So that's its growth rate. And it's growing at 2% each year, but if we want to figure it out, it's 100%, which it costs now, plus the 2% we're increasing, times time. So that's my equation. And I'm trying to figure out how much it's worth in 2015. Now it's since 2010, so it's been 5 years. Plug in a 5 there. And we're going to figure this out using our calculator. It's an application problem. So bring out your calculator. 1500 times my growth rate, 1.02, 2% higher than my normal cost, to the 5, because 5 years since. So $16,561. So roughly $16,561. So it's grown up in value by almost $1.5 grand in 5 years. Pretty good. Next example, same idea. A virus spreads to a network of computers such that each minute 25% more computers are infected. If the virus began at one computer, graph the function first hour to spread the virus. So here's my formula. Right, A is the initial amount, which in this case started at one computer, so that's 1. My growth rate, 25% more computers are affected each minute, so 1 plus R, which is 1 plus 0.25, so 1.25. T. Now the problem I wanted to figure out how much to spread in the first hour. So they want me to graph in the first hour. Like, we'll do a basic graph here. We could do it. Plus 0, so my horizontal slope is at 0. I'm crossing out, A is 1, so I'm going to cross out 1. And my B is 1.25, so it's a growth. So again, we're just doing a sketch that looks kind of like this. I'm actually more interested to figure out how many computers are affected within the hour. So let's plug in 60. I want to figure out what that is. How many computers are affected in the first hour? So 60 minutes is an hour. Plug in 60. Use your calculator. 1 times 1.25 to the 60th power. And you get over 600,000 computers are infected over the first hour based on this virus. So that's how you do it. That's how we do exponential growth. Next up, exponential decay. So what's that? Decay is when the B value is less than 1. So we can do an example like y equals 1/2 x. So you can see the difference. Let's go like -5, -1, 0, 1, and 5. So I get 1/2 to the -5 power. That does, it flips it, right? So 2 to the 5th power. So 32. 1/2 to the -1 power flips it, you just get 2. 1/2 to the 0 power is 1. 1/2 to the first is 1/2. And then 1/2 to the 5th power is 1 to the 5th, which is 1, 2 to the 5th, which is 32. So we have that. If we graph it, -5 goes to 32, so it's way up here. -1 goes to 2. 0 goes to 1. 1 goes to 1/2, so it's like right here. And then 5 goes to 1 over there, which is right up 0. So you see it's like the opposite of the one we just did. It goes like that. That's a decay graph. It's just where you do not want your stock market to go, right? It's dying. It's a decaying. So that's what a decay graph looks like. So a decay graph goes down. So it crosses that one initially. And like before, it has a horizontal slope at 0 and you can't cross. So in side effects. So again, went through all of it. Other than that, we graph it the same way. So let's do a couple examples. This first one here. Again, B is a decay. So decay. So I know it's going to go down. My A is 1. My A is 2. So initially it crosses at 2. My horizontal asymptote is at -4. That's how much my whole graph's moving down. 1, 2, 3, 4. So that's where my asymptote is at. right? And then what I'm doing is I'm moving my whole graph down 4. So you can go start at 2, I'm going down 4, so I'm right here. But then I got to move it inside opposite right 3. So it's going to go 1, 2, 3. So right here. That's the kind of the crux of my graph, right? So I'm gonna, now again, it's a decay graph. So I'm going to go down here, I'm going to hit it, and I'm not going to go past that line. I shouldn't go past the line, then go past the line, hopefully. So something to that effect. Again, it's a sketch, it's not supposed to be perfect, I just want you to be able to sketch it. If I wanted to be a little nicer graph, I could always find the y-intercept by plugging in 0 and see what happens. So that's a decay graph. Domain and range, domain, all real numbers. Range, low to high, my lowest is -4 to infinity. So that's where that goes. Next one's a little tough. Next one has a flip to it. Besides the fact that it's all fractions. So how do we go with flips? So generally you're supposed to flip first. That's kind of always the case. Now here I actually do it. Normally most of the time I don't, but in this case I actually do. So I want you to be able to see what flip looks like. So normally, right, it's a decay graph looks like this. It's my best attempt with that. We're going to flip it down. So I'm doing this so you can see the graph, right? So we're flipping it down. So it's actually look like this. So that's what my graph's going to look like. It's going to kind of be going up. It's actually a growth now. And if a flip does do that, it switches it from growth to decay. So it started off as a decay. But now you consider it a growth graph. It's going up from left to right. Anyway, this graph is like normal. So my A is at -1/3. So you can start there if you want. At -1/3. My vertical shifts at 3. So that's my horizontal asymptote at 3. Right? Because that's always horizontal. So that basically means you get that point, you move it up 3. Or if you want, you start up -1/3 below the horizontal asymptote. So either way, I'm right here. Then I gotta move it inside opposite. I can move it right 4. So 1, 2, 3, 4, like around there. Right, and I just gotta draw it. Now again, normally it looks like this, but since I flipped it, it actually looks like that. That's the picture I'm trying to get. So it's just a sketch. If I wanted a nicer graph, I could find the y-intercept and stuff, but something to that effect. My domain, all row numbers, -infinity, +infinity, right? Left to right, all arrows. My range is a little interesting. Lowest is an arrow this time, -infinity. My highest was that 3? So -infinity to 3. Okay, let's do an application problem and then we could start off, finish off. Same idea, we do the exact same way as before, right? A is initial value. B is the growth factor. And again, or in this case it's called decay factor. Growth decay factor, I could say sometimes. You always start at 100%. Sorry. And then if it's a decay factor, you lose your R. If it's a growth factor, you gain your R. And T is time. Other than that, that's do the exact same way. So this is this problem, we can finish off. An SUV depreciates in value each year by a factor of 15%. So that's my R. Make it a decimal. Draw a graph SUV value in the first 20 years at the initial purchase. So my formula is going to be this. I need my R. My B, sorry. Remember, B is always 100%, so 1. In this case, it goes down in value, so minus 0.15, which makes B 0.85. And I need my initial value. Now, it's kind of hard, I don't tell you here, it's in the picture. 20 grand. So Y equals 20 grand times 0.85. So you only get to keep 0.85 of your initial value every single year. And where normally we get to keep more than, right? When it's a growth, we get to keep more than 100%. That's the whole idea. So in this case, we want to get to keep 85% of the value. So we have that. If I want to graph it, we're not a graph. It starts at $20,000 up here somewhere. And it's a decay, so it's going to go down. It's my terrible decay drawing. A couple things I want you to point out though, even with this. Notice how it's +0, so it can never go below 0. Which makes sense. You can't sell a car for negative money. And you can't sell a car for 0 either, right? That's just free, giving it away. So you can't sell a car for negative or $0. So look at that. Now again, like before, I'm actually curious. How much does this car cost now after 20 years? So you bought it 20 years ago, apparently, for 20 grand. So let's plug in 20. Let's put into our calculator. See how much it actually costs. I'm very curious. So let's go on 20 grand times. We want to get to keep 85% of the value each year to the 20th, and it's worth about 800 bucks. So in 20 years, you buy the car for less than $1,000. That's a lesson.